All right, welcome back to the Deep Dive. Today we're taking a look at something that's, well, it's pretty crucial for the future of conversational AI. It's all about how we can get those AI agents to handle really complex tasks and do it all, smoothly and accurately.
Yeah, definitely a hot topic right now.
So the paper that caught our eye is Performant LLM Agentic Framework for Conversational AI. Alex Kasella and Wang are the authors.
Oh yeah, I saw that one come across my feed. Definitely piqued my interest.
Everyone's talking about large language models, right? These LLMs are like the brains behind a lot of these AI agents we're interacting with more and more. And this paper really digs into how we can get them to navigate those intricate decision-making processes. Think of it like following a really complex flow chart to get something done.
Right, exactly. And not just any flow chart, but specifically in the context of conversations.
Yeah, so like voice assistants, chatbots, that kind of thing.
Precisely. And the authors, they don't shy away from pointing out where things can get tricky with current methods.
Yeah, they lay out the challenges pretty clearly, don't they?
They do.
Okay, so two main things they highlight, right? First is accuracy, making sure these AI agents stay on track, no going off on tangents or spitting out nonsense, what they call alignment errors or hallucinations.
Yeah, those are classic LLM pitfalls.
And the second is efficiency. Nobody wants to wait forever for the AI to figure out what to do. So minimizing that lag, the latency, as they call it, that's a big deal.
Huge, especially in real-time applications. Imagine you're on the phone with customer service. You don't want to be on hold while the AI is churning away trying to figure out the next step.
Absolutely. So that's where their big contribution comes in. This new system called the Performant Agentic Framework, or PAS for short.
And what's cool about PAF is that it's not just another incremental tweak. It's really a different way of thinking about how the LLM makes decisions within these workflows. It's like giving it a more structured, logical compass to guide it.
I like that, a logical compass.
Instead of relying solely on the LLM's sort of free-flowing understanding of language, which can be amazing, but also prone to those errors we were talking about.
Right, so more precision, less wandering off into the AI weeds.
Exactly, and potentially much faster, too. So the potential here is huge, especially for those really complex business environments where reliability is paramount.
Right. Okay, so let's unpack how they actually do this. Let's break down the paper a bit.
Right, sounds good.
So they start off by, setting the stage, emphasizing just how common these graph-based workflows are. I mean, they're everywhere, right?
Oh, yeah, they really are. Once you start thinking about it, you see them everywhere.
Like for our listeners, imagine, a flow chart. You got boxes representing actions or information and arrows showing the different paths you can take based on certain conditions. That's basically a graph-based workflow.
Right. A classic example is those phone trees you get stuck in when you call customer service. Press 1 for billing, press 2 for technical support, and so on.
Exactly. And the paper gives some really good examples too, like a healthcare call center, figuring out where to route your call based on the kind of insurance you have.
Oh, yeah, I remember that one.
Or tech support agent trying to, walk you through those sometimes endlessly complicated steps to troubleshoot your internet connection.
Been there, done that.
And they have these, they actually have these figures 1 and 2 in the paper. They visually show how these seemingly simple interactions can turn into this whole web of decisions.
Yeah, they do a great job of illustrating the complexity.
Right. So it's pretty clear these workflows are really important for all sorts of things.
For sure.
But here's the thing, right?
Yeah.
LLMs, amazing as they are at understanding language, they weren't really built for this kind of rigid step-by-step process, especially when you throw in, a lot of contextual information, a lot of history to the conversation.
That's the thing, right? They can get lost in the weeds if you're not careful.
So the traditional approach to get around this, as the paper explains, has been to tack on a separate planning phase. Like, have the LLM first figure out the entire sequence of actions it needs to take before it actually starts interacting.
Right, okay, I need to gather this information, then check this condition, then maybe do this action, kind of like plotting the entire route on a map before you start driving.
But as we all know, adding that extra step can introduce a lot of lag. And in a real-time conversation, that's a killer.
Yeah, that's where latency becomes a real problem, especially in, voice interactions where things need to flow naturally.
Okay, so the authors have laid out the challenge, right? How do we get these AI agents to accurately and efficiently navigate these complex workflows without adding a bunch of delay? And that's where PAF comes in.
Right, PAF is their answer to that challenge.
But before we get into PAF itself, they do a nice job of kind of putting their work in context. They look at what other people have tried.
Yeah, I thought the related work section was really interesting.
So they talk about these existing agentic frameworks like LangChain and LangGraph.
Uh-huh.
And those are, essentially toolkits that developers use to build these AI agents. They often rely on this technique called prompt chaining. It's basically like, the output of one prompt to the LLM becomes the input for the next one.
Right, kind of like a chain reaction.
But what's really insightful is their critique of these methods. They point out that while they're flexible, the way they use keywords to trigger different actions can lead to errors, especially in those really complex workflows.
It's like trying to find your way through a city using only landmarks. It might work in a small town, but in a sprawling metropolis, you're going to get lost.
Yeah, a good analogy. And then they get into context window limitations. This is a common issue with LLMs, right?
Oh, absolutely.
Where they can lose track of information or even start hallucinating details that aren't real.
They start making things up because they've forgotten what was said earlier, or they've just drifted too far from the original context.
And that's a big problem for these complex workflows where, everything needs to be consistent.
Right. It can lead to those alignment errors they mentioned.
Okay, so then they broaden their view a bit. They look at, the overall research landscape in conversational AI.
And it's a pretty active field, right? Lots of different approaches and techniques being explored.
Well, they make an interesting point. Well, there's a lot of focus on things like handling different kinds of input, like text and voice. They call that multimodality. And on building in safety measures, those guardrails we hear so much about, they argue that there's still this gap when it comes to ensuring consistent accuracy in those real-world scenarios that involve, a lot of branching logic, those if this then that situations.
Right, like those complex decision trees we were talking about.
Okay, then they dive into Meta-GPT, which uses these predefined standardized operating procedures, or SOPs.
I've played around with that one a bit.
Yeah, so the idea there is to use those SOPs to guide the agents, make sure they're following company guidelines and all that.
And it can be pretty effective for certain tasks.
But the authors point out that the way Meta-GPT works with its iterative planning and validation steps can really slow things down.
Yeah, it's not exactly known for its speed.
So it's not ideal for those real-time voice applications. They also mention that it can struggle with unexpected user inputs and those really long, extended workflows.
And because it often requires fine-tuning for very specific domains, it's not always easy to generalize to new situations.
Okay, so they've laid out all these limitations of existing approaches, right? And they're essentially positioning PAF as a way to overcome these hurdles. Instead of relying so heavily on the LLM to figure out every single step, they're introducing this more structured, almost algorithmic way of making decisions within the workflow.
So more guidance, less free-for-all.
Exactly. And that brings us to the heart of the paper, the Performant Agentic Framework itself. And they describe it in two flavors, you could say, basic PAF and optimized PAF.
Right, so like a base model and then a souped-up version.
Okay, so basic PAF. The core idea here is to use the LLM as a kind of judge.
A judge. Interesting.
Yeah, so the LLM's job is to constantly figure out where the agent is within that decision-making map at each point in the conversation.
So kind of like a navigation system.
Exactly. And they have this whole algorithm 1, which they call LLM as a judge, which details how this works. It involves, carefully formatting the conversation history, providing the LLM with what they call contextual anchors, basically saying, okay, you were here, and these are your possible next moves.
So giving it some breadcrumbs to follow.
Yeah. And then the LLM, it analyzes all this and identifies the current location within the workflow. And then the system parses and validates that response against, that predefined map. So the key takeaway here is that basic PAF is shifting that heavy lifting of deciding the next step from the LLM's, sometimes unreliable reasoning to a more structured evaluation of where it is in the process.
Makes sense. So it's not just letting the LLM wander around freely, it's giving it some guardrails.
Okay, then we have algorithm 2, the basic agentic framework, and this takes that LLM as a judge concept and actually puts it into action in a continuous loop.
So like the operational side of things.
As the LLM is, generating its response to the user, the system is using algorithm 1 in the background to figure out which step in the workflow the agent has reached.
Ah, so it's constantly checking its location.
And this then triggers any actions associated with that step and updates that internal map accordingly.
Okay, I'm starting to see how this all fits together.
And they emphasize the modularity of this. By separating that language generation part from the workflow navigation, they can do things in parallel to speed things up. like using a separate service to convert the text to speech if it's a voice interaction.
Right, because that text-to-speech conversion can take some time, so doing it in parallel saves you valuable milliseconds.
They also point out that this step-by-step approach actually reduces errors compared to trying to cram everything into one massive prompt.
So breaking it down into smaller chunks makes it more reliable.
All right, so that's basic PAF, but then they go a step further with optimized PAF.
Optimized, so even better.
Well, it's optimized for certain kinds of workflows, specifically those really intricate ones where you might have multiple steps that sound very similar but lead to completely different outcomes.
I can see how that would be tricky.
And in those cases, the agent could easily get confused, even with that LOM as a judge method.
So they needed something extra to disambiguate those similar sounding steps.
Exactly. And that's where optimized PAF comes in. It introduces this vector node search algorithm 3.
Okay, vectors. Now we're getting into some more mathematical territory.
But it's actually a really clever idea. So you know how we've been talking about embeddings?
Yeah, those numerical representations of words and phrases.
They're basically a way to turn words into these numerical codes that capture their meaning. And this allows the system to compare them much more precisely than just looking at the surface level words themselves.
Right, because words can have multiple meanings and the context matters.
So they vectorize the instructions associated with the current step in the workflow, the instructions for the possible next steps, and the latest response from the user. And then they calculate how similar these vectors are.
Makes sense.
And a key point here is that they're using the dot product as their measure of similarity.
Dot product, why that specifically?
Well, they cite some research that shows that it's particularly good at capturing those subtle nuances of language, those little distinctions that can make a big difference, especially when you're dealing with, specialized terminology or jargon.
Ah, so it's like a more sensitive similarity measure?
Exactly. So by bringing in these vector embeddings, they're adding this whole extra layer of semantic understanding to the decision-making process.
So it's not just about matching keywords anymore, it's about understanding the underlying meaning.
And if the highest similarity score is above a certain threshold, then the system can confidently identify the next step based on those vector similarities.
So it's like a shortcut, if you will. If the vectors are a good match, you don't need to go through the whole LOM as a judge process.
Exactly. But if the scores are too close or below the threshold, then it falls back to that more careful evaluation method.
So it's like a safety net, making sure it doesn't make a hasty decision.
Okay, and then algorithm 4, the optimized agentic framework, basically integrates this vector-based node search into the whole process.
So it's like the conductor orchestrating all these different components.
And they even pre-calculate all those vector embeddings for, all the possible steps in the workflow ahead of time to save processing time during the actual conversation.
Smart. So they're doing the heavy lifting up front to make the real-time interaction smoother.
All right, so that's how PAF works. But, the real question is, does it actually work?
Right, the proof is in the pudding.
So to test it out, they ran a bunch of experiments. They compared both basic and optimized PAF against a baseline approach, which was essentially just throwing the whole conversation into one big prompt and letting the LLM figure it out.
So a more naive approach, basically.
And they simulated these conversations based on, predefined workflows. And then they evaluated the responses using metrics like semantic similarity, which is basically how close the AI's response was in meaning to a pre-verified golden response.
So how well did it understand what it was supposed to say?
And they also looked at the percentage of responses that hit a very high level of similarity.
So not just average performance, but how often did it nail it?
And the results are they're actually pretty impressive.
Yeah, I was surprised by how well it performed.
So their tables 1 and 2 and figure 3 in the paper, they show the data, and they found statistically significant improvements in how semantically similar the responses were when using both basic and optimized PAF compared to that baseline.
So both versions of PAF were better than the naive approach, but was there a difference between them?
Yeah, that's the interesting part. Optimized PAF also significantly outperformed basic PAF.
So those vector embeddings really made a difference.
It seems so. Really highlight the value of that approach. And, kudos to the authors. They made their code and the scripts they used to generate the data publicly available.
That's always great to see.
Yeah, really good for reproducibility and for other researchers to build on their work.
Open science at its best.
Okay, so in their conclusion, they do a nice job of summing up the main benefits of PAF.
Yeah, it's a pretty compelling list.
So first, it speeds things up by, reducing the need for all that extra planning and validation we were talking about.
So less back and forth, more streamlined decision making.
Second, it improves accuracy by following that step-by-step logic, making sure the agent stays on track.
Fewer chances for those alignment errors to creep in.
Third, it reduces the amount of information the LLM has to keep in mind at any given time by focusing only on the relevant parts of the workflow.
So it's like decluttering the LLM's mental workspace, making it more efficient.
And finally, it reduces the number of times you have to actually call the LLM by using those vector-based scores for those quicker decisions.
Less computational overhead, more bang for your buck.
And then, thinking about the future, they outline some really interesting directions for research.
Yeah, I liked their ideas for future work.
Like assigning different weights to different steps in the workflow, or creating more flexible rules for how the agent can move through the process.
So more fine-grained control and adaptability.
They also suggest exploring how PAF could be used with different kinds of LLMs, like those specifically trained for certain industries, and fine-tuning those embedding models and scoring methods for specific tasks.
Yeah, tailoring it to the particular domain or application.
They also include that, standard statement about the potential impact of their work, advancing the field of machine learning and agentic workflows.
Always good to highlight the broader implications.
Okay, so to kind of put this all in perspective, I want to take us back a bit, to the history of conversational AI.
Okay, a little trip down memory lane.
So back in the early days, it was all about those really rigid, rule-based systems. Those early chatbots that could barely handle a simple question.
Yeah, very limited, very brittle.
And they couldn't deal with the nuances of natural language at all. Then came statistical NLP and early machine learning.
That was a big step forward.
Definitely gave us more flexibility, but those systems still struggled with managing those complex multi-turn dialogues, keeping the conversation flowing naturally and consistently.
They were better at understanding, but not so good at actually conversing.
And then LLMs came along, and that was a huge leap.
A game changer for sure.
They gave us this unprecedented ability to understand and generate human language. But as this paper shows, even these powerful models have their limitations when it comes to those tasks that are inherently structured, that require that precise logical navigation, especially as those tasks get more and more complex.
Right. It's like we have this amazing engine, but we need a better transmission to harness its power effectively.
Yeah, good analogy. And PAF feels like, it feels like an important step in developing that kind of framework for building those more reliable LLM-based systems, particularly for conversational AI.
It's like moving from just having the raw ingredients to actually having a recipe for how to combine them into something delicious.
So if we think about the key takeaways here, what really stands out to me is that PAF's innovation is this smart blending of symbolic reasoning, the well-defined logic of the workflow, with those sub-symbolic methods, those vector embeddings, and similarity scoring.
Yeah, it's that hybrid approach that makes it so powerful.
And this addresses the weaknesses of both, those purely LLM-driven methods, which can go off the rails, and those old-school rule-based systems, which are just too inflexible.
It's like finding the sweet spot between flexibility and control.
And then their emphasis on the dot product as a similarity metric, that's not just a minor technical detail.
No, it's a deliberate choice that reflects their understanding of the nuances of language.
It's about being able to detect those subtle semantic differences that can make all the difference.
And the experimental results really back that up, showing clear improvements in accuracy without sacrificing speed.
Making PAF a much more viable option for real-world applications.
Yeah, it's not just a theoretical concept, it actually works in practice.
Okay, so, stepping back and thinking about the bigger picture, the implications of this are pretty huge.
Yeah, it's exciting to think about where this could lead.
Just in customer service alone, imagine AI agents that can handle those truly complex and personalized interactions, like dealing with, unusual return situations or updating customer relationship management systems during a sales call, all with much greater accuracy.
And much less need for human intervention, which could free up human agents to focus on those really tricky edge cases.
And think about healthcare.
Yeah, lots of potential there.
TAF could enable more efficient patient triage and information gathering while still strictly adhering to, all those medical protocols.
And in technical support, it could guide users through those convoluted troubleshooting steps with much more precision.
And, it's not just limited to customer service. Any field that relies on navigating those intricate decision trees or structured processes could benefit. Financial services, legal procedures, education, you name it.
The possibilities are pretty vast once you start thinking about it.
Okay, so now for our novel notion statement. where we like to, kind of speculate a bit, think about where this research could go.
Always fun to explore the what ifs.
So one thought that popped into my head was, what if we explored dynamically adjusting that similarity threshold used in PAF's vector node search?
Dynamically adjusting, so not just a fixed threshold.
Exactly.
I like where you're going with this.
So imagine, a customer support system using PAF. And suddenly there's this massive spike in calls because of, let's say, a product recall.
Okay, so a very dynamic situation.
The types of questions coming in might shift rapidly, and the language customers use might change too, as they're reacting to the news. And that fixed similarity threshold in PAF, as it's currently designed, might become a problem.
So it might not be sensitive enough to those shifts in language and context.
If the language shifts even slightly, the system might miss the correct next step because the similarity score dips below that threshold.
Ah, so false negative, essentially.
Or, conversely, if certain phrases that are, ultimately irrelevant become really common, you could see false positives.
Where the agent gets sent down the wrong path because it latches onto a phrase that's suddenly popular but not actually relevant to the task at hand.
So my thinking is a one-size-fits-all threshold might not be the best approach in those dynamic situations.
So how would you go about exploring this idea? What kind of research could shed light on this?
Well, I think it would be interesting to look into dynamically adjusting that threshold based on real-time analysis of, the incoming user queries, like looking at the distribution of those vector embeddings within the workflow map. You could probably use some statistical methods to detect those shifts in the semantic landscape and then adapt the threshold accordingly.
So like a self-tuning system that adapts to the changing environment.
Exactly. And you might even, draw inspiration from research in anomaly detection in embedding spaces or those adaptive control systems. A PAF system with this kind of dynamic threshold could be much more resilient, perform well across those diverse and changing conditions.
Yeah, that's a really cool idea. It highlights how a system like PAF, even though it's already a big step forward, still has room to grow and adapt to those real-world complexities.
For sure. And that's what makes this field so exciting. There's always more to discover and improve.
Absolutely. Always pushing the boundaries.
All right, so to wrap up our deep dive into Performant LLM Agentic Framework for Conversational AI, I think we've seen how this paper presents a really novel approach to guiding those LLMs through those complex workflows. It's all about combining their reasoning abilities with that more structured mathematical approach using those vector-based scores.
And the results really speak for themselves. Significant improvements in accuracy, speed, and efficiency.
If you're interested in digging into the technical details, the link to the full paper is in the show notes.
Definitely worth a read for anyone working in this area.
And, I think it's important to step back and think about what this means for the future of conversational AI, for how we build and deploy these increasingly sophisticated agents.
Absolutely.
And those ideas we were just talking about in our Novel Notions segment, they just scratch the surface of the potential here.
There's so much more to explore.
All right, thanks for joining us for this deep dive into some really cutting-edge machine learning research. We'll be back soon with another insightful look at the latest advancements.
Until next time.
See you then.